Welcome. This video is going to look at the last part of Section 2 from Chapter 3, or the end of Chapter 3 from the Brown SL Chemistry book. And here they're going to look at the periodic trends among chemical properties or chemical behaviors of the different elements. So the bottom line is chemical properties are determined by the electron arrangement and the valence electrons in an atom. And because elements are arranged by their valence electrons into similar groups or families, that elements in the same group or family are going to have similar chemical properties. Not an accident. Chemists tend to look at the properties of group 1, 17, and 18, which are the alkali metals, the halogens, and the noble gases, because this is the most reactive metals, the most reactive nonmetals, as well as the non-reactive elements or the noble gases. Chemists also tend to look at period 3 and the trends that happen because it doesn't involve transition metals, but it does involve metals, metalloids, and nonmetals to do some comparisons with. So these three families and the one period will allow us to look at the basic chemical behavior for S and P block elements. So not going to cover everything out there, but we're going to cover a pretty good chunk of chemical behavior. So group 18 is really the first one to look at because the unreactive noble gases tell us a few things by their non-reactivity. They were among the last elements discovered because they're colorless gases, they're monoatomic, and they're very unreactive, so who knew they were there? They have complete outer shells of 8 electrons, with the exception being helium, which has only got the 1 energy level, so it's full at 2. And their inability to gain or lose electrons is explained by their full shells. Their full shells give them the highest ionization energy, so they don't easily lose electrons. Their full shells also gives them a very low electron affinity because if they gain electrons, they're going to have to go into a new shell where they'd be even further from the nucleus with very little attraction to the nucleus, so those electrons are going to be easily lost. There's also no reason for them to enter into a covalent or ionic bond because they're already stable, and so they're not going to have much electronegativity for any kind of covalent bond that they might be forced to form. So then the other 17 families have reactivity because they don't have complete outer shells. So their incomplete outer shells make them unstable, so they're going to tend to lose or gain electrons to achieve the electron arrangement of the nearest noble gas. Groups 1 to 3, which are metals, generally lose electrons because it takes less energy. Not because they have fewer electrons to gain or lose, but those electrons take less energy to lose. They are large atoms with low electronegativities, low ionization energies, so it's just more energy efficient to lose those electrons. Groups 5 to 7 are the smaller nonmetals, and so they have high electronegativities, high ionization energies, so it's more energy efficient to gain electrons. And then period 4 is where you have got some metals, some nonmetals, and we see both gaining and losing going on within group 4. So let's look at group 1 called the alkali metals. They're silvery metals. Most metals are silvery. They're too reactive to be found in nature uncombined, so you don't find pure sodium or pure potassium or pure lithium or pure rubidium. They're always combined with something, some kind of salt, chlorine, sulfate, whatever. If you actually have them in pure form, you have to store them in oil because they will react with just the water vapor in the air and certainly with the oxygen in the air. Physical properties of the alkali metals, they're good conductors of electricity. Remember, this is all about the delocalized electrons in a metallic bond that allows them to be good conductors. They're also good conductors of heat. They have low densities compared to other metals. And they have a gray shiny surface when freshly cut. Now that shiny surface only lasts a very small time because they will start oxidizing with any oxygen that comes in contact with them. Chemical properties, they're very reactive because they're low ionization energies. They're going to form ionic compounds with nonmetals, and so we generically represent this group as M+1 since it's going to lose that 1 electron to become stable. And the reactivity will increase down the family because they get even larger, so they have even lower ionization energies as you move down towards cesium and francium. A couple things you should know about alkali metals as far as how they react. They react with water to produce hydrogen and then a metal hydroxide. The resulting solution is basic or alkali, so that's where they get their name from, is the alkaline solutions they form. And this reaction becomes more vigorous as you move down the family. And again, that's because the metal itself becomes more reactive. So when you put pure lithium into water, it floats and fizzes and eventually completely reacts. When you put sodium in, the sodium actually melts into a liquid drop which floats and also fizzes and moves around. Whereas with potassium, it actually ignites and burns with kind of a pinkish flame. And by the time you get to rubidium and cesium, even small amounts will ignite explosively and create a lot of heat and gas as that happens. So the basic reaction for any alkali metal is Li plus H2O gives you LiOH and H2. So it's really, if you think about H2O as HOH, it's really a single replacement reaction with Li bumping off the H to form the LiOH, and then the H2 going to its elemental form of H2. It's most stable as H2 rather than H plus ions. And so you could substitute in Na, K, Rb, whatever. It's going to be the same basic reaction for any of the alkali metals. Group 17 at the other end, the halogens, they exist as diatomic molecules, so they're generically represented as X2. Their physical properties are that they have colors. Unlike the noble gases, halogens have distinctive colors. They change down the family from being gases for fluorine and chlorine to being a liquid for bromine and being solids for iodine and astatine. And remember, that makes sense because more electrons, as you add the energy levels, increases the van der Waals forces. So that's going to change the state at the same temperature. Chemical properties, they're very reactive nonmetals. But this decreases down the family because the atoms get larger, so the electrons are further out and harder to hang on to, and the nucleus is tucked further in, so it's harder for it to attract new electrons to the atom. They also form ionic compounds with metals, or they'll form covalent compounds with nonmetals. And they're generically represented with an X minus to show their -1 oxidation state. Their reactivity is due to their readiness to accept an electron because their outer electrons have a high effective nuclear charge, the greatest for any element in a period. And so that high effective nuclear charge of +7 plus their small size is going to give them a strong ability to attract other electrons. So, logical question is, how do alkali metals and halogens react? Really easily. Halogens react quite easily with group 1 metals to form the generic MX, so NaCl, KCl, KF. It's always a 1-to-1 ratio. The resulting electrostatic force between the positive 1 ion and the negative 1 ion forms an ionic bond, holds them together, and the most vigorous reaction between the alkali metals and halogens would be with fluorine, the most reactive nonmetal, and then cesium or francium, the most reactive metal. The reason I say cesium or francium is, again, because francium is so rare that it's not really available for comparison. There's also something called the halogen activity series, and you may remember the metal activity series, where different metals, more reactive metals, can bump off a less reactive metal in an ionic or aqueous solution. Well, the same thing is true with halogens. And you can determine the reactivity of halogens with each other by having a single replacement reaction between a halogen gas, or the pure halogen, and then a metal halide, or one of the alkali metals bonded to a halogen. And you often can tell if the reaction occurs or not because there'll be a color change that accompanies it. So the more reactive element, if it's the one that's there as a halogen gas, it will bump off the less reactive element from the ionic compound and put it back into its elemental state. So if a reaction happens, the more reactive halogen ends up as an ion, and the less reactive element ends up as the halogen gas. And the reactivity is known to decrease down the family as the atomic radius increases, or the distance between the nucleus and electrons increases. Another thing you should realize is all the halogens form insoluble salts with silver. So anytime you react a halogen, say with silver nitrate, you're going to form a silver halide that's going to precipitate out as a solid. And so then it's easy to identify the halide or the halogen with this precipitate. Okay, so that's enough about the families. How about period 3? What trends do we see as we move from metals to metalloids to nonmetals? Well, the transition is often shown with the period 3 oxides, and that just means how the period 3 elements combine with oxygen. So period 3 metals are going to combine with oxygen to form an ionic compound because you have a metal and a nonmetal. Silicon, which is a metalloid, forms what's called a giant covalent structure with oxygen, and carbon in family 4 does the same thing. So it's not an ionic compound, but it's a little different than most covalent compounds. It's this giant covalent because it's got 4 bonds going and is a very strong covalent structure. But then the rest of the nonmetals, phosphorus, sulfur, and chlorine, are just going to form molecular covalent structures, diatomic, possibly more than diatomic, but fairly weak structures. And then, of course, the noble gas, argon, isn't going to form an oxide at all. So the trend across is to go from a very ionic character to a covalent character to, a pure covalent, almost a pure covalent character to no bonding at all with the noble gas. So you're moving from a stronger to a weaker bond. And if you look at the difference in electronegativity, you see you go from a large difference in electronegativity, meaning it's very ionic, to a very small difference, meaning it's very close to being a true polar covalent bond. And an easy way to test for how ionic a bond is or a substance is you dissolve it in water and check the conductivity. Ionic compounds, of course, should have good conductivity, whereas the covalent compounds, even as aqueous solutions, will not have much conductivity, if any at all. The other thing that's often done with period 3 is to look at the acid-base character, and specifically, what happens when you put these period 3 oxides into water? Do they take on an acidic or a basic nature? Well, remember, acids are defined as containing H plus in the most simplest form, and bases are defined as containing OH minus. And again, this is a simple definition of acids and bases, but it works for us with period 3 oxides. The other thing to remember is water is really HOH, or H plus and OH minus. I know it bonds covalently technically, but it really is a fine line between whether it's a covalent or an ionic substance. So think about it as being HOH, or a positive and negative ion, and then predicting what happens to your period 3 oxides is much easier. Okay, the acid-base character of these oxides directly related to their bonding and structure. Because metals have M plus, when they break off from their ionic compound, then they're going to have to combine with the anion or the OH part of the water molecule. Nonmetals come off with a negative charge. They're the anion, so they're going to have to, they're the anion. They're going to have to combine with the cation or the H plus part of the water. So it's not a big surprise that metals end up forming bases, nonmetals form acids. And then metalloids are what we call amphoteric. And since they're from group 4, the silicon, the carbons, they can form either positive or negative ions, so they could combine with either the OH or the H plus. So the metals, what you have to know is 2 basic reactions that happen with the metals. The first one's really easy. When a metal oxide combines with water, it just simply combines to form the hydroxide, the base. So Na2O plus H2O forms 2NaOH. MgO with a plus 2 charge with H2O, it forms MgOH2. So really not difficult to figure out what's going on here. It just simply combines or synthesizes in a very simple equation. When you put the basic oxide with an acid, then you get a neutralization reaction, and as we get to acid bases, you'll remember that. So Li2O plus HCl is really, again, this one's a double replacement reaction here instead of a synthesis. The Li and the H are going to trade places, so I get LiCl, and then I'm going to be left with H2O instead. And then the same thing happens with the MgO, forming MgCl2 and H2O. So a synthesis reaction and a double replacement reaction going on here. or at least those are the simplest forms to think about it and keep straight what's going on. So looking at nonmetallic oxides, even if you have SO3 with no charge on it, SO3 can easily become a polyatomic ion with a 2- charge on it. So when it combines with H2O, this simply combines or synthesizes to give you H2SO4. The extra oxygen becomes part of the sulfate ion. With Cl2O7, this is a little harder, but again, the O is going to join onto this group, so I'd have Cl2O8, which really would be the same as 2 chlorate ions, ClO4. So they're pretty easy to figure out. The amphoteric ones are a little odder. Your book talks about aluminum. And the idea of aluminum oxide is that when you put it in water, it doesn't really do anything because it doesn't dissolve in water. So instead, you can add it to an acid or base. And when you add it to an acid, it forms AlCl3 plus 3H2O, showing that it's able to react with acids. But it really doesn't become acidic or basic. But if you put it in with a base, then it does form a strong base, AlOH4. And I apologize for the mistake here, but the product should be 2AlOH4. And I don't have a good, clever way to remember this, but just remember amphoteric is not true acid or true base like the metals and nonmetals are.